This is the most exciting time in my entire career. And I think that is a result of the questions that can be answered today that we couldn't answer before.
We're able to see connections in areas that once seemed totally separate. The openness and sharing of big data, whether it's in research or medicine, is sort of doing the same thing.
The future of health is really already here. Few people in the general public probably even know. Take all this data, take it apart, and turn it into knowledge which would help give us insight into disorders that affect Americans every day.
Big data is this new term that we all use. Every time you go to your doctor, he or she draw bloods, they ask you questions, they measure things, and classically they wrote it on a piece of paper. And it's the notion of now putting that into data elements, and data elements that we can search.
Big data is not just the number of individuals that are in your sample, but it's what you're actually collecting.
So from one drop of blood now in our lab routinely, we put it through a superconducting magnet, and we get a 50 gigabyte picture of all of the proteins in the blood. That's gigabytes of data that are moved from a machine to a place that it's stored. A decade ago, nobody was putting into a computer what happened on a daily basis in our business. Now we all are. We're incentivized to. We do it every day on every patient.
A lot of the big data that we gather anymore is a consequence of some of the technology that's available to collect it. So you might imagine that some device maker allows you to collect biomedical data in a particular way. We'll give you new insights into biological processes, what goes wrong in health and disease.
A scan could be collected about you, an MRI scan, and that could be compared in a database electronically to hundreds of thousands of other examples and used as a diagnostic aid by the clinician to fully understand where you belong in that population.
This is sort of an unprecedented amount of information, whether it's from the electronic health record or from imaging or genomics. There is so much data that it's impossible for a single human or even an army of humans to look at all of the data. We do need these automated techniques, and often these techniques will find patterns that a human would not.
You'd be able to, say, incorporate people's health records into this information, find out, oh, you have a genetic disposition for a particular disease. Do you live in an area of the country where other people also do?
Genes work in an environment. Some of the environment is in our head. Some of it's in the city that we live in.
The real revolution in data is we can start to categorize cancer. So instead of just lumping it by where it came from, we're going to start to personalize how we understand, how we categorize, and how we treat disease. 2 to 3 times a week, I look at someone in the eye and say, I have no more drugs to treat your disease. And I don't want to do that anymore. And if I could tell a patient there's hope, I've done a tremendous thing.
Ultimately, what we would want is to really figure out a cure or figure out primary prevention. You stop the disease before there's ever any evidence of it developing for a given person.
So historically, collecting data was difficult, and we had very few data points. But the more data points we have, the better the answers we're going to get, and the more accurate those answers are.
The technology will be able to gather all that information on millions of people.
Almost going from a really big perspective, but because of having so much data, being able to drill it down to one person.
And so you can say, okay, this type of medicine, this type of exercise, this type of food works for this kind of person.
Pediatric asthma is one of the projects I look at, just trying to figure out what's causing asthma in these children and being able to understand both their environment and what they're doing in their daily activities that might actually trigger an asthma attack. Collect that information and subsequently analyze it and figure out, can we predict ahead of time this child is going to be in a situation where they are prone to an asthma attack and prevent it?
There are things that we've come to think we've understood about what's good for us with it's bad for us, that I think once we have enough data to be able to look at some of these trends, we'll actually be able to get clarity on whether or not these things are true, whether or not we were mistaken 20 years ago when somebody made this recommendation, and now we can, for the betterment of the health of the country, we can make different recommendations based on having the availability of more data.
The hope is that we can utilize those insights to actually then tailor healthcare.
That will allow us to come up with personalized prescriptions for individuals.
Targeting therapies or treatments specifically to you and how you live and what your physiology is like. There are efforts going on within the BD2K program to create these kind of consortiums that will gather data, share it with everybody, combine it, and use it to understand healthcare issues. This is really kind of becoming a worldwide phenomenon. I think it transcends a lot of political boundaries.
There's probably just under 100 different projects from groups around the world that participate with us, not only in terms of aggregating the data that is collected there, but also to understand what these data are telling us and to understand health and disease. And we do this by applying imaging techniques and combining them with other observations. That means that we get the advantage of having virtually unlimited resources to recompute and to manipulate these data to obtain information from it.
Taking lots and lots of data, distill it down into something that people can use. Data scientists have a particular job of turning it into graphics that are informational, that convey information, and you're systematically turning it into pictures or representations, render it in such a way that it becomes interactive, or that people can very easily and almost at a glance be able to understand what that big data is telling them.
We've made great advances in heart disease, cancer, where we've actually been able to reduce the number of deaths associated with these diseases, but not with Alzheimer's disease. Currently in the US, there's 5 million people living with Alzheimer's disease. Now we can actually use brain imaging to view the Alzheimer's pathology in the living human brain. And in fact, these parts of the brain are actually starting to deteriorate. We can keep them active. An exciting avenue for my research is to try to develop really refined, targeted types of virtual reality environments. We can make it challenging. We can add obstacles if we need to add obstacles. We can actually modify or personalize the environment given that person's current capacity.
Aggregating data of tens or hundreds of thousands of people really gives us insight as to a disease process that we didn't have before. It identifies biomarkers that were not available to us, and it also allows us to track the trajectory of a disease over time, either interrupting that as a result of an intervention or just watching the decline of an individual with enormous fidelity.
As a nutritional epidemiologist studying nutrition and cancer, I can access genetic data on NCBI dataset that's readily available. That data is not going to be able to be run on my desktop. So I would actually have to take that, use an external workflow.
We also keep somewhere in the order of 5 petabytes of data online. It allows us to have at our fingertips images from tens, if not hundreds of thousands of patients, but also genetics. So both of these data sources are large, and we can combine them and relate them in ways that were unimaginable only a short time ago. This is great for not only developing the technology, but also bringing together scientists from around the world.
My involvement with big data is translating discoveries that my colleagues in the lab are making to the public who doesn't really have exposure to the specifics of the work that we do. The techniques that are being used right now weren't even thought of 5 years ago.
As a researcher, I'm going to go out and ask people to, give me their data. And I'm going to use that in my particular study. One of the interesting challenges with big data is how do you bring them all together? There's a lot left to be done. Certainly with the sharing of data, getting over some of the sociology. People are a little very protective of their data, and rightly so. They've worked hard to collect it, and they should have kind of first crack at it. But really, once that data is available, share these with open access repositories so that others can take that data, look at it in new and clever ways across databases, combine it with other data, and test new hypotheses that I didn't even think of.
Everybody in the medical world has to use the same words, the same dictionary, because it allows things to be merged together. And so we need to standardize how we collect the data, how we term the data, how we describe it. All of those things, if we standardize and all do the same thing, the large databases will come. And we'll be able to cross data from one institution to another, one researcher to another. And progress, instead of going like this, will go like this. All of us allow our data to be used, and we use data in the right way to advance the field. So you're going to contribute to the database and you'll get something back.
So we started this program called GAIN, which really is a global interactive network which describes Alzheimer's disease data that's been collected independently for different projects around the world. And the reason you want to do this is the statistical power requires vast numbers of observations.
What are the patterns and the relationships across data sets to really target specific questions? All of this data will also go back and contribute to big data. It will go into our repository here and be widely shared with the world.
One of the challenges we're going to have is how the information's used. I think a lot of people are rightly concerned about security and privacy.
There needs to be a conscious effort, and it's one that we're very good about at the Institute. Implementing privacy controls into the system. People need to feel that they are safe and that their information is not going to be used against them.
All institutions do take steps. All scientists have to go through this training of securing data, ethical collection of data, storage of data.
This is an era where data is accessible, and so we need to get better data security.
In doing that, we can preserve the integrity of the initial agreements that people signed up for when they said, yes, you can use my data, or yes, I'll participate in this study.
There's always going to be concerns about personal health information and about how that's handled. Those things will get sorted out as people realize that this has a personal benefit to me to make sure that I can be identified with my data.
As information technologies and things like big data become prevalent tools that we utilize, patients will want to become more involved. Trying to understand how patients are going to become part of their healthcare is a huge issue. It's something that we are only beginning to touch upon.
We can't modify one's age. We can't modify one's genetics. But we know that there's other factors about the way that one lives that can be changed. And say, let's see if we can get these on a better trajectory for your future.
If you come in and you tell me, listen, I'm tired, first question I ask, how much are you moving today? What are you doing? All of a sudden, there's a device in your pocket that has all that information. And the power of this new data revolution is your data is portable.
We will be integrating aspects of what we call mHealth or mobile health. And so all of the participants in our study will have different monitoring devices that they will wear that will give us information about their activity levels, what their heart rates have been.
When I got my first device to look at movement over time, I was shocked how much it was sitting. I would have told you, I walk around 6-7 hours a day.
You can look at your diet, your nutrition, physical activity, your heart rate.
They're able to measure your pulse oximetry, and record this throughout the day.
Because we have the Fitbit, we have the apps, all of these other technologies more readily available, then individuals can become more responsible and aware of their own health.
Cedars-Sinai here in Los Angeles now lets patients upload information from their iWatch. And that information is captured into their electronic medical record.
Because people are not dependent on an external person to help them figure these things out, and because it's so readily available for them, there's definitely an incentive for individuals to say, I can change my own health and I'm in charge of my own health.
We have these crazy computers in our pockets that we carry around all the time that do a lot of things that we know how to use, but not really how they work.
We can actually look at tweeting about different activities. Whether it's Instagram, Twitter feeds, all of these are sort of pictures into a patient and their life and their behavior. People are trying to collect as much objective information about what they do in their daily activities and put numbers to it so you can understand it as it evolves over time. That type of information, as extreme as it might seem in some cases, is the perfect sort of understanding, though, of why we actually develop disease.
What we need to do is to start to say, what does society need? What do people need to improve healthcare? And that's how we start to have to change training.
There is a tremendous interest for students who want to study this. We've got this advent of information, but if we don't have users who understand how to look at this data, how to access it, those discoveries will not actually come to fruition as quickly, maybe.
Training the next generation of scientists who are coming up in data science techniques and technologies. They need to be prepared early so that they know how to handle the ever more data that we're going to collect.
And that's a very big step for medical school to say, listen, I'm going to take a portion of our curriculum and make students learn this. That is about the future, not the present. On average, it takes about 12 years for 50% of doctors to adopt a new technology. It's a skill where we don't have great training programs in the country. There are a few. We need a lot more.
Data science being this kind of weird amalgam of computer science, statistics, mathematics, and even computer graphics.
You need to have the computer scientists to help with developing those technologies that can utilize these data. But then you need the scientists to answer the questions. This is very multidisciplinary, and you need all the players on board in order to develop an effective curricula.
Coming up with majors and academic programs specific for data science in our universities. And that's one of the things which is important about the big data to knowledge enterprise that the NIH has kicked off. They're really recognizing that data isn't just this byproduct of these great biological hypotheses, it's the coin of the realm, and that really to embrace data as a challenge and part of the future of biomedicine, it's a very important step.
Bring up a new generation of doctors who are effectively utilizing things like social media and health information technologies to work with their patients.
The idea that there's a static body of knowledge, we need to teach that there's this canon of unchanging things, is going by the wayside with the pace of change in technology. But really what is going to be important is the ability to adapt to the new things that are coming down the pipeline.
Training the next generation of investigators requires that they're given the best tools, the best experiences, and understand that cross-disciplinary experiences are essential to being successful.
The revolution in data and the ability to collect data is going to allow us to look at you and I as what we call a complex emergent system, because that's what we are. Disease in the body is part of a complex emergent system. It's not looking at one lab value or one element, it's looking at all of them together. And the big data revolution to me is just that.
One of the goals eventually of our institute is to aggregate the largest set of brain images across the world. And through really trying to pursue big data, we'll start to make even more discoveries.
Data collection, data storage, the sharing, the whole big data thing in biomedicine is not going away. It's here. Certainly the support of government organizations like the National Institutes of Health, the National Science Foundation is absolutely critical.
The revolutionary ideas today in big data are going to be the things that my kids grow up taking for granted, completely unable to imagine the world prior to their existence.
The new hope in the room is not a new medicine, but it's big data. I want to be out there, on the forefront, really pushing is let's liberate the data. Let's get it out there so we can all benefit.
It isn't going to slow down, and it isn't going to stop, and it isn't going to change. It's only going to get better and better.
We can work hard to gather the data here, put our minds together, put all of it back into our big data center for the rest of the world to think of new hypotheses, new questions that we didn't think of asking, and probe that data to be able to make new big discoveries.
It's just so exciting every day. There's just something new happening. The pace of discovery is accelerating.
As we move forward as a scientific community, and I hope that our congressmen and congresswomen are paying attention to this. This is where new science gets done. This is where cures will be found.